It's recording now. This is week 7 written homework problems. We're going to go over problems 1 through 4 for torque, and it's solely torque. What's missing from this written homework is going to be like the angular acceleration, angular velocity stuff. A lot of that is covered in the online. Now, it's unfortunate that they don't cover it in the written, but if I have time at the end of the session, I'll go over the online. Usually I want to go over the online now because I know we want to focus more on the concepts since that last exam. But if I'm not able to go over any of the online problems this time, I might hold another session tomorrow or just cover as many online homework problems on Tuesday during the quiz session as part of the review. But yeah, so I'll go ahead and get started now with problem 1. So problem 1 is merry-go-round shenanigans. Tom and Jerry both push on the 2-meter radius merry-go-round as shown in the figure on the right. Tom pushes with a force of magnitude 30 newtons, and then the pivot is that black dot shown at the center, right? So we have Tom and Jerry, right? This is the only type of problem that's goofy that I like because Tom and Jerry is quality TV right there. I don't like the Among Us problem that they had on the last quiz, but I do like this one. So we have Tom's force, so we can say like F Tom. This is really tension, but we can just say F Tom. That's 30 newtons, right? We don't know what F Jerry is. We don't know the force for Jerry. But we also know that the radius is 2 meters. You have access to that information, and the pivot is right here in the middle, right? So the concept of a radial line, like, right, since we're doing torque problems, the concept of a radial line is just a line that's along the radius of the circle, right, or along the radius. That's why they call it a radial line, right? So it's just kind of, it forms a radius, and that's why we denote it R. On either side, so it could be radius this way, radius that way, right? It's a length, right, extended from the center axis, right, to any force that you want. So if you have a force here, you could have one like that. If you have a force there, you can have one like this. So it's just a line, call it the radius, right? It just goes from the axis to the force in question, and it has to cross through the force. So like has to cross through this force here. So if we have a force applying here in this direction or in this direction, whatever, the radial line has to cross that force. And so you can see here the radial line crosses the force at Jerry and at Tom as well. So we denote basically this position to kind of be 0. That's the axis. So this would be like 0 meters. And then your radius, your radial line being 2 meters, that would mean that 2 meters is here, right? To the left, that's Tom's position, and 2 meters there, that's Jerry's position, right? And we don't denote it like -2 or +2, it's just 2. So just 2. Now, we want to figure out what force should Jerry push with so that there's no net torque on the merry-go-round about its center. So if there's no net torque net, and I like to call this fancy T because, I mean, it's tau, I guess, but whatever. Yeah, so this is fancy T, net torque is 0. Yeah, so 0 torque. Anyway, we want 0 torque, and in order for there to be 0 torque, right, if Tom is exerting some torque and Jerry is exerting some torque, then in order for them to be 0, then torque for Jerry has to equal torque for Tom, right? That only makes sense. If Tom is exerting a torque, Jerry has to exert kind of an opposite torque in a sense to where they cancel each other out, and the merry-go-round is not moving at all, right? It has 0 torque applied on it, total, net. So now we have to think, well, we know torque, the concept of torque, right? You can either have like positive or negative torque, right? Like you can have a positive or negative force. So there's different notations though for positive and negative when it comes to torque. So for torque, I like to think of it as a clock, right? And an alligator. So if you have, these are your minute and hour hands on a clock, for example. If the alligator's mouth opens like this, right? You're going counterclockwise. Then the torque is positive. Now, if the alligator closes its mouth back up, goes back to the positive x-axis, and this is where the alligator analogy kind of fails anymore because there's just no other explanation for this. But now if you go counterclockwise, I guess if it opens its mouth really wide, like if the bottom like mandible, I guess, opens itself lower somehow, let's just think about that, okay? Then essentially you're going clockwise, and so clockwise is negative torque. So forget the alligator for a second, and let's just go by counterclockwise and clockwise. So clockwise is negative torque, and counterclockwise is positive torque, right? So that's our notation for torque, clockwise and counterclockwise. So if you're going counterclockwise this way, right, if the force that you're applying helps push the merry-go-round in a counterclockwise fashion this way, right, then it's positive torque. Oops. And if it's going clockwise like this, right, as time does on a clock, then it's negative torque. So we want to look at now Tom's torque right here. What direction is that going? If imagine you're pushing, right, if you're pushing this way on the merry-go-round, what direction is that merry-go-round going to go? Clockwise or counterclockwise? Exactly, right? So if you go counterclockwise, right, because if it pushes it like this, kind of pushes it down, so then that whole merry-go-round goes this way, and you can see that's counterclockwise, right? Now Jerry, on the other hand, he pushes down like this. So what would his direction be? Clockwise, right? Yeah, exactly. So you're pushing down like this, you're going like that, clockwise, like clockwork, right? So clockwise is negative, counterclockwise is positive. So Tom, we know, has a positive torque because he's kept going counterclockwise, and Jerry has a negative torque because he's going clockwise, right? Now, once again, oh, not T Jerry, my bad. This should be T net. T net is equal to T Tom minus T Jerry, right? And then we already said that T net is equal to 0, right? So T Tom should equal T Jerry. So we have T Tom is equal to T Jerry, right? So we know the equation for torque is F R sine phi, not theta, phi. And so this is force from Tom, by the way. This is force from Tom, so let me denote that real quick. F Tom, so that should equal F Jerry R sine phi, right? So for Tom, we know that he pushed with 30 newtons. We know the radius here, they're on the edges of the circle, so the radius for both is going to be 2 meters, right? But they push at different angles. So the angle here is also important, and so really there's a really easy way that I think about it. And so I think about the angle that you use, phi, being the angle that's sandwiched in between the force and the radial line. So I have this 60-degree angle here, right? Now here's my force like this. Here's my radial line. The angle that I use is the angle that's sandwiched in between, that touches, right, both the force and the radial line. It's this angle right here, sandwiched in between the force and the radial line. Well, how do I get this angle right here? Well, if you kind of go back to geometry, if you've taken that, or if you kind of have, I guess, maybe some intuition, then you know these are vertical angles, right? They're about the same. So that means this is 60 as well, right? Alternatively, you should know that this is a straight line, right? So this is 60 degrees. So this would make it 120 here, because 60 and 120, that gives you an 180 degree angle, or a straight line, right? And then this is another straight line along the force, right? So this is 60 as well. So that's a longer route, or alternatively, you know that vertical angles from geometry, they're equal to each other. So if this is 120, this is 120. If this is 60, this is 60. That's just a longer way of doing it. But yeah. So this should be 60 degrees here for our phi, and that means that this is 80 degrees as well for phi, for Jerry. So we have all information that we need. We know that Jerry is 30 newtons, or Tom is 30 newtons, times a radius of 2 meters, times sine of 60 is equal to force of Jerry times 2 meters times sine of 80, right? And that's how we can figure out Jerry's force. We're interested in his force, not his torque, right? If they just asked us for torque, well, we know that torque of Tom minus torque of Jerry has to equal 0 because there's no net torque. Net torque is 0. So then if you just calculate this part, you should be able to get Jerry's torque. Otherwise, if you want the forces that are relevant to each, then you have to kind of expand this out and write torque as Fr sine phi, Fr sine phi. And then you solve for your forces here. So force of Jerry should end up being around 26.38 newtons. And then you also have to indicate, right, that this is a negative force. Why? Because in this case, our end value that we get here for F Jerry, right, that's going to give us the magnitude, right? And so we should have a negative sign there to add to indicate that the direction that he's going in is going to be that clockwise direction. For Jerry, yep. For radians, that's going to only be like your angular acceleration, angular velocity stuff. That's when you'd convert an angle to radians. So you go from degrees to radians in that case, if we're doing angular velocity, angular acceleration type problems. But if we're doing torque type problems, you stay in degrees. Yeah, so for Jerry, both the torque and force are negative. So torque is dependent on force, the radius, and the angle here, right? So we denote force being negative or positive based on the direction that the object is moving in. So like we said, if he's pushing in a clockwise direction, you're going to have a negative torque. If it's counterclockwise, it's positive torque. And so clockwise or counterclockwise, negative or positive, that's what we're going to have for our forces. Because our sign is, or like our angle is going to be positive. Our radius is going to be positive no matter what, right? Now the difference here is just the force. So we have to make the force negative to make it clockwise and a negative torque. Because when I'm solving here, I do T Tom minus T Jerry is equal to 0. I integrated the direction right here from the beginning. So when I set them equal to each other and I find out what F Jerry is, I get a positive force. That's just the magnitude. When I integrate my direction in the equation, I can put in magnitudes for all my values. Now, in order to get the actual force, because they're asking for the force, not the magnitude, I have to add a negative sign at the end to indicate that yes, there is a clockwise torque provided by Jerry that allows a negative torque, and that negative torque right here exists because of a negative force, basically. Does that make sense? Yeah, so clockwise you have a negative force and therefore a negative torque. Counterclockwise, positive force, therefore a positive torque. Yep. And this is literally the same kind of concept with like the net forces that we were doing in the last couple of weeks. So if this was like F Tom, for example, minus F Jerry, right? And you set them equal to each other. If Tom was, so Tom was 30 newtons, right? So Jerry has to be 30 newtons as well. But if they cancel out, one has to be negative, one has to be positive, right? So that's that kind of intuition there. But yeah. Now, for part B, it's saying in order for the net force to be 0, there must be a force F pivot exerted on the merry-go-round at the pivot. Calculate the x and y components of this force. So, we know that net torque is 0 here, right? Net torque is 0. There's no rotational motion being provided that's going to make this merry-go-round turn. However, there are some forces, right, that are being applied to cause that torque, and they aren't fully canceled out yet, right? So I have a force downwards like this, and a force downwards like that from Jerry and Tom, and a force right from Tom, and a force left from Tom. So maybe Tom's force to the right cancels out Jerry's force to the left. But since they're both applying a force downward, or they have a component of their forces downward. So this might be like a negative 20 Newton, for example, and this might be negative 10. So there's a net negative 30 Newtons, for example, downwards along the negative y-axis, right? So we must theoretically have another force directed at the pivot here that would apply a force that would cancel out those forces, right? So it must be like, for example, a positive 30 Newton force to cancel out the negative 30 Newtons ones. So basically, we're just trying to figure out how the forces cancel out. Now, how the torques cancel out, how the forces cancel out now. So you have components in the x direction, and you have components in the y direction. So that's what we're figuring out here. So we can set up a F net y and an F net x equation to figure out how the forces cancel each other out. So we have here F net x, right? And that's equal to F Tom minus F Jerry, right? Because Tom pushes to the right, Jerry pushes to the left. And then let's say this is an unknown force, so let's say this is F3x, right? Now, we know that Tom's force was the 30 newtons, right? Jerry's force was the negative 26.38 newtons. But since I've already included the negative sign here, I can just say that it's 26.38, right? I don't throw in an extra negative and make it negative 26.38. I just take that negative and place it here. So it's 30 minus 26.38, and then that's plus F3x. And we know that we want the net force to be 0 for the components, so this should all equal 0, right? So if we solve that, we should be able to get our F3x, right? So F3x in this case would actually be directed along the negative x-axis, right? We should get somewhere around negative 10.4 newtons, I believe. And let me calculate that out just to be sure. Actually, no, wait, hold up. I see where I went wrong. My bad. Forget what I said here for a second. So I made the mistake of just integrating or putting in the forces. Yeah, go ahead, Matthew. Yep, exactly. That's why I went back and I was like, all right, I made a mistake there. I should have calculated the components. For some reason, I put in the just the overall force and not the components. So that's my mistake. But yeah, F Tom X and F Jerry X. That's the mistake I made. So for F Tom X, right, force of Tom in the X direction would be 30 newtons times, well, let's see. We have this angle right here. This is his x direction. So this should be cosine 60. So 30 newtons cosine 60 will give us the x direction for Tom. And then 26.38 newtons. And this is, here's the x direction, right? So this is adjacent. So this should be cosine 80, right? And then plus F3x. There we go. And that's equal to 0. So yeah, you find out the components. My bad. I just went ahead and calculated using the overall forces instead of the x components. That's my bad. But yeah, that now should give you an F3x of around negative 10.4. Does that make sense so far? Okay, cool. F net y, on the other hand, same deal, except that now we're going to be doing things in the y direction, right? So we have Tom is negative and Jerry's negative, since they're both pushing kind of downwards, right? They have a negative y component to their forces. So it should be like negative F Tom y minus F Jerry y. And then we don't know the third force here, right? And the reason why we put negative here is because obviously This is pointing in the negative direction, and I want to integrate the direction in the equation from the beginning. It's just easier that way. Can you explain the F3x part? So F3x is the third additional force that we want to calculate, because they're saying there must be a force F pivot. I just put F3x, so yeah, this would be F pivot technically, exerted on the merry-go-round at the pivot. There's X and Y components to that force that help make the net forces 0 overall. Does that make sense? Cool. But yeah, all three of those forces, basically, like whatever Tom and Jerry are applying, they're not giving rotational motion. They're not giving you a net torque. That torque is 0. But their forces still don't cancel out. So there must be a third additional force at the pivot that has an X and a Y direction that'll cancel out the forces totally. So, and like I said, yeah, negative F Tom Y and minus F Jerry Y here, because they're both directed along the negative Y axis. They have negative Y components, basically. And so we have here negative F Tom, that's negative 30 newtons. And this should be sine 60 now. It should be minus 26.38 newtons, sine 80, and this is plus F3Y, and that's equal to 0, right? Because if you go back and look at the angle, here's our angle, here's the Y direction, that's opposite to the angle, opposite over hypotenuse, that's sine, right? So we want to do minus 30 newtons to give us that negative aspect of the Y component of Tom's force. So it's negative 30 newtons times sine 60 minus 26.38 newtons times sine 80. And then we want to figure out what our Y component of the pivot force is here. So if we calculate that out, that should give us an F3Y of 51.96 newtons. And that makes sense, right? That kind of, at least maybe this portion might not be as clear, but for sure this makes sense in the context of the problem, right? If they're both pushing downwards, then there must be a really big force pushing upwards, right? That will help cancel out the downward forces that they're exerting, right? Now, if you kind of look at the shape here, you can see that the X direction for Tom is a lot bigger than the X direction for Jerry. So if we were to leave it at that, you can see that there's a positive force in the X direction, because Tom's X component here is bigger than Jerry's X component. So we would have an additional force that's pointing in the negative direction that we can see here that would kind of help Jerry out and cancel out Tom's X component, basically. Does that make sense overall for problem 1? Why is the net force for Tom and Y is negative? So Tom's force is negative here because you can see here he's directing a force like this, right? It's along the, here's positive Y, here's positive X. It's along the negative Y axis. So that's why I include a negative sign here at the beginning. I just like to include my signs in my equation. Alternatively, you can just say like F Tom Y plus F Jerry Y plus F3Y is equal to 0. But then you'd have to throw in your negative signs when you're calculating. That might throw you off. And so I just like to include the negative signs in my equations. So then I can just put in the magnitudes of the forces. But yeah. Sound good so far for problem 1? Any questions at all? All good? Yep. Okay. So problem 2 now. Tension in the deltoid muscle. When we hold a weight at arm's length at the height of our shoulder, the deltoid muscle is largely responsible for keeping our arm and the object at their fixed height. To estimate the tension in the deltoid, we model the arm as in the drawing below, with all forces acting on the arm at the indicated distances from the origin, right? So we have different forces here acting on the arm with different distances from the origin, and the origin here is pretty much like at, I guess, the scapula essentially, or at the origin point of the deltoid muscle. So the arm's mass is 10 kilograms and its weight, Fg, Earth on arm, acts on the center of gravity, while the small object's mass, this little weight here, right, is 6 kilograms and exerts a force. They consider it as a normal force in a sense, and that's the weight on the arm, right? And the reason why they call it a normal force is either there's a surface of contact between the arm, or the hand basically, or the arm and the weight. So they consider it like a normal force in a sense. Don't know why. I guess that's just the notation that they want to give you for it. But the deltoid then exerts a force at an angle of theta is equal to 15 degrees. This is tension of deltoid on arm. Now, we really don't have like a lot of information right here with like forces and stuff. We do have indications of how we might get forces, right, with different masses, an indication of weight, right? But let's find out. So it says for all questions below, torques are measured relative to the origin, and counterclockwise rotations are positive. So counterclockwise is positive, clockwise is negative. So what is the torque in Newton meters exerted by Fg Earth on arm? So Fg Earth on arm should just be the weight of the arm. So this is just what is the torque exerted by the weight of the arm, right? The arm has a certain weight, it exerts a certain torque, right? And that's what we're trying to figure out. So, and just keep in mind, I haven't like really looked at this problem, so bear with me, and please keep an eye out if you do see something that you're confused about, or you feel like maybe something's gone wrong, like especially with that problem here. Thank you so much for those who pointed that out, that I messed up the components, so stay vigilant. So we have FGEA, right? And that's equal to mg, right? And that's the mass of the arm times the acceleration due to gravity. So the mass of the arm was 10 kilograms. So that's 10 kilograms times 10 meters per second squared, easy 100 newtons, right? Now if we want to figure out the torque of the arm, basically. Yeah, go ahead. Mm-hmm. I see what you mean. So when we're calculating torque, we want to look at the forces that are directly contributing to that torque. And so torque, remember, is Fr sine phi, right? So there's a force exerted at a certain distance, right, with a certain angle. So if you look here, the distance for the center of mass of the arm, right, the center of mass is just going to be straight in the middle here. So the torque exerted by the arm, essentially, is going to be a component of its weight, the weight of the arm, the distance it is away from the origin, right, from the scapula or the origin of the deltoid muscle, and then the angle at which that force is exerted. So the reason why we don't include the weight here is that it's at a different distance. It's at 72 centimeters instead of 36. So when we're looking at torques exerted by different objects or entities, right, we're concerned with not only like what is exerting a force that is going to give us a torque, but also like where is it exerting the force that's going to give us a torque. So they're at two different locations, and that's why we don't integrate them together. Now, theoretically, if that ball is like right there on top of the center of mass, then yes, we would have to factor in both, I guess, technically. But even then, I wouldn't like combine them together and say like Fg is equal to 16 kilograms times 10 meters per second squared, because you would just find out the force, like the torque for each entity or object alone, and then you can add up the torques if you want to. That's kind of what we're going to do in the upcoming parts. It's just that, yeah, when you're calculating torque, despite any other objects that might be acting and giving torques elsewhere on the radial line, right, we only look at the torque and look at the force exerted here based on the distance as well. So this is 36 centimeters away. The ball is 72 centimeters away. And so we're also given a force here where they're specifically asking us just for the force of gravity, the weight due to the mass of the arm, basically. That's why they denote it here FGEA as opposed to FNWA here. So they made, first of all, an indication that they're only interested in that mass of the arm giving us a certain weight, giving us a certain torque. And then in the separate part here, they're asking us specifically just about the actual ball here. Does that make sense? So back to the torque of the arm. If they want us to calculate the torque of the arm, we have the force of gravity due to the arm, right? That's FGEA. And it exerts that force a certain distance away along the radial line. That's 36 centimeters. That's 0.36 meters, right? And then sine phi, well, it's directed immediately downwards like this. So the angle that's sandwiched in between the radial line and the force is just a perpendicular angle here, right? That's going to be 90 degrees. And sine of 90 is just 1. So here would just be 100 newtons times 0.36 meters, right? So that should give you 36 Newton meters for your torque, I believe. Is that looking like it makes sense for everyone? The only thing that then I would add, yes, excellent. Who said that? All right, excellent job, Matthew. Yeah, it's negative 36 Newton meters. And that's because it's going downwards like this. So if I think about this as being like a hand on the clock, right? This is a one huge weird clock. But if I go this way, pulling it downwards, it goes in the clockwise fashion, right? And clockwise is negative. So we should add a negative 36 there at the end. Make sense? And let me move this upwards a little bit so it doesn't interfere with the next problem. But we're going to do the same thing basically for the weight here at the end. It's just that now we're going to factor in the object's mass, which is 6 kilograms. So FNWA, that's 6 kilograms times 10 meters per second squared, right? So that's 60 newtons. We have torque due to the weight, I guess, or I'll say ball, just easier that way. They say it's a weight, and it kind of throws things off. So ball, and that's normal force of the ball, right? Weight on arm, and that's times 0.72 meters, and that's also times sine 90, because directed perpendicular. Here's the angle that's sandwiched in between the radial line and the force, right? Here's that angle right there. So that's 90 degrees. Sine of 90 is 1. And we use the radius here, the full radius, which is 0.72 meters. So we just look at the entire distance here, 0.72, the location of where that force is acting. Would you just say torque of the arm, like torque FG? I would, like for part A, you mean? Yeah, I would just say torque of the arm. Just torque of the arm. But yeah. And that's here for torque, for part B here, torque of the ball or torque of the weight. And so this is just 60 newtons times 0.72 meters times 1, right? And then we obviously have to add a negative sign at the end. So we should get around negative 43.2 Newton meters. Right? That should be our torque of the ball. And once again, it's negative because if we were to think about this as one big like clock, right? Here's the hour arm or minute arm or whatever, right? And we have directed downwards like this, so it moves like this, right? In a clockwise fashion, and clockwise is negative for torque. So we have negative 43.2 Newton meters. Does that make sense so far? Cool. Now for part C, it says for the arm plus object system to be static, what is the torque exerted by the deltoid muscle? So by static, we mean static equilibrium, right? And we'll get into this like in the coming week here. They're going to talk a lot more about static equilibrium, but static equilibrium for an arm and object system just means that the torque is going to be 0. So we have a force here exerting torque, a force here they're exerting torque, and a force here exerting torque. When we add up all the torques for each one, they should equal 0. That's essentially what it's saying. And especially for complete static equilibrium, not only do your forces or do your torques have to cancel out, but the forces have to cancel out as well. So it says if the system is in equilibrium, what is the magnitude of the tension force as well? Right, so we're going to figure that out here in a sec. But with regards to just the torque having to cancel out and become 0, well, we know that T net is equal to 0 because that's a net torque of 0. That's when it's completely static, right? 0 torque is applied. And that's going to be equal to, well, let's look here. We have a negative torque from this force right here and a negative torque from this force right here because they're both going in the clockwise direction. How about Ft? What direction is it going? Counterclockwise, right? Excellent. So counterclockwise. So that's going to be a positive torque. So we can say torque of the deltoid, right, minus, let's say, torque of the arm. And instead of, maybe just to play it safe, instead of torque of the arm, just in case they just go crazy about the notation stuff, you can just literally just put torque of the force in question. So like torque of force of gravity earth on arm. So you can just be like torque of force of gravity earth on arm like this. It's a lot, but I would maybe prefer this notation because then you're not playing it dangerous with regards to the notation of the forces. And then you have torque of normal force of the weight on the arm, right? So how do we know it's counterclockwise? So once again, just think about if you had your arm extended like this and someone pushed your arm like that. If your arm was like a hand on the clock, would you be going counterclockwise or would you be going clockwise if they push your arm or pull it like this? That's how I always think about it. Like, imagine, jeez, if your hand or that rod that you're, acting or causing acting a force on, right? So if you're having that force of tension act on that rod or that arm, right? If I were to literally like pull that arm in that direction or push a minute hand or hour hand on a clock in that direction, would I be going counterclockwise or clockwise? That's how I would figure it out. And so if I literally pull my arm, like imagine this, here's my arm, right? And I bring it this way, because I pulled it upwards like this, up and to the left. Then if this was a clock with minute, hour hands, right? And if I go essentially backwards in time, that would be counterclockwise. Does that make sense? Yep. But yeah, I think that's just probably the easiest way. Think of a clock and maybe think about like, yeah, really, that's why we say counterclockwise or clockwise. Just the clock stuff is really important. But yeah, I would literally just think of you manipulating, like if your clock was faulty or something and you just had to like adjust the time, right? If you had to push the minute hands or the hour hands in the counterclockwise direction, oh, I pulled it kind of up and to the left, basically, right? So I just kind of think about it that way. And so counterclockwise, like we said, is positive. Clockwise is negative. That's the notation. So our deltoid muscle is the only one that's going to be providing a counterclockwise direction, and that's going to be positive. The rest are pulling us downwards like this. So this was a clock. They're pulling us downwards in a clockwise fashion. So that's why they're both negative there. So in this case, T deltoid will just be equal to the combination the addition of both of these forces together. So TFG plus TFN, basically, right? And so this should just be, what is it, 36, I think was the other one. Yeah, 36 Newton meters plus 43.2 Newton meters. That should give you an overall torque for the deltoid of 79.2. And remember, when I integrate the directions here, I just plug in the magnitudes, just the magnitude. I forget the negative sign because I already put it here. So this would be like saying minus 36 and minus 43.2. And so when I add those over, you can see it's 43.2 plus 36. And that should give you a positive torque there, which is going to make sense because it was pulling in the counterclockwise direction. So this should be 79.2 Newton meters here for the deltoid torque. But yeah. Now, if the system is in equilibrium, right, like we said, if it's complete static equilibrium, not only does the torque have to be zero, but the forces have to be zero, right? And so now we're interested in, okay, well, if this is the torque needed to have static equilibrium, right, to have the forces all kind of cancel out, then what is the magnitude of that force that is going to be giving us a torque? So torque deltoid has to be equal to F deltoid, or F tension, basically, that it's causing at a specific distance away along the radial line at a specific angle, right? So if we look at here, it's at 0.18 meters or 18 centimeters away. It's directed along an angle of 15 degrees, right? That's the angle between the radial line, sandwiched in between the radial line and the force, sandwiched in between, right? 15 degrees. And then that's how we can figure out our tension, because we know that this is 79.2 Newton meters. We want to figure the F tension force out. It's directed at 0.18 meters or 18 centimeters away, and it's at a sine of 15 degrees, right? So that's how we can figure out the F tension force. And that should be around 1700 newtons. And so basically, if this whole thing is 1700 newtons, right, it's going to have an X component and it's going to have a Y component. Now, being 1700 newtons, it's going to offer us an X and a Y component that will directly cancel out with the Y components here. But then you have to look, well, okay, there's a Y component force that'll cancel out these other Y components. But then there's this extra negative X force, basically. Well, what do we do about that? Well, that's where E comes into play, right? That's where E kind of comes into play. Because this 1700 Newton force, well, is going to be applied. And I actually kind of jumped the gun a little bit because I don't know for sure if this Y component of the tension force is going to fully cancel out these other forces. It could. Maybe it couldn't. We've yet to find out. But basically, for part E, they're asking us now to look carefully at the free body diagram. The system can't actually be in static equilibrium because the sum of the drawn forces is not zero. There must be force on the arm acting at the origin, exerted by the scapula, and they want us to figure out the X and Y components of the force. And you can see that because you have these Y forces directed at the bottom, you have a single force here directed at the top, and you also have a negative X force. Well, we don't know about this force. This could very well cancel out these other forces in the negative Y direction, but you definitely have an X component force that's not canceled anywhere else. And so the origin, right, the scapula itself would have to exert a force along the X direction, specifically the positive X direction, to cancel out the negative X force caused by the deltoid muscle from the tension. So this is just a matter now of kind of setting up F-net equations instead of net torque equations, right? Because we want to figure out how all the forces add up, or how do they cancel out to all equal zero at the end and actually give us static equilibrium in real life, right? So we know that in the y direction, F net y, we have F tension pointed upwards here along the positive y-axis. So Fty. We have an Fg and an Fn, right, from the weight and the mass of the arm here. And then we have just an unknown force at the origin, right? You have an unknown force at the origin, but those are all going to equal 0. Now, it's just a matter of filling these out, basically, right? So for Fty, pretty simple, right? We have, this is 1700 newtons. We have our angle. If we want to figure out the y component here, we can just do trig. So this is the y component. We can do sine of 15 because it's opposite over hypotenuse, right? So 1700 newtons times sine of 15 degrees, right? And then minus, this was what, 100 newtons, right? And it's also minus 60 newtons, right? And we don't calculate any components for these because they're directed immediately along the y-axis, right? And we're only interested in the y-axis right here, right? So it's not directed at an angle or anything. Technically it is directed at a 90-degree angle, and so if we wanted to, we could say like 100 newtons times sine of 90, but sine of 90 is 1 anyway, right? So it's directed, like if this was our y-axis here, you can see that this force here is directed at an angle from the y-axis. So we want to figure out Fty. But these forces are directed immediately along that y-axis, so you don't need an angle really to calculate for them. So it's just 100 newtons to 60 newtons, just equal to the magnitude of the gravity there and the normal force for the weight. And then it's obviously just plus the force that's exerted at the origin at the scapula, right? To cancel everything out. And so we can go ahead and calculate everything out here, and we can see that Foy, right, the y component of the force at the origin should be equal around negative 280 newtons, right? So that's our F net y force along the origin there. Now, this is F net y. Let me make this a little bit smaller. Now I'll leave it up to you guys to figure out F net x. Anybody want to walk me through it? Or anybody have an answer for it already and want to explain? So you're close. It's just that the only mistake that you're making here is that these forces don't have an x component, right? Their x components are zeros. So so we don't even include these in our equation actually, right? But yep. And excellent. So it is negative 1700 as well because it's directed along the negative x-axis, right? So that's absolutely correct. And then you just have to add it to like an F origin x, basically. So negative Ft cosine 15, right? Because this is along the negative x-axis. It pulled it up and to the left, right? And then plus some unknown force along the origin in the x-axis, right? So in that case, if this is all equal to 0, right, because they have to cancel out, then the x component of the force on the origin should just be equal to 1700 newtons times cosine 15. And then that's equal to 1642.1 newtons, right? So that makes sense because if that is the only force, that tension force is the only force that's applying a force in the x direction, and it applies it in the negative x direction, then there must be a force at the origin here that's going to apply it in the positive x direction to cancel it out. Sound good so far? Any questions at all about problem 2? Nope, no questions. Cool. That kind of brings us now to problem 3. So problem 3, yeah, this is, once again, never seen this one before. So playing it dangerous, but hopefully everything works out okay. So problem 3 is balance and stability, once again factoring in torque and forces and stuff. So it says, consider the situation below with a boy walking along the beam, resting on 2 supports, just resting on them, not physically attached. The beam is uniform with a mass of 70 kilograms and has a length of 5 meters, and the boy has a mass of 45 kilograms. So the beam itself has a mass of 70 kilograms and has a total length of 5 meters, and the boy has a mass of 45 kilograms. The supports here are 3 meters apart. So from here to here is 3 meters. And the boy here is 0.4 meters away from the right-hand support. The system is in static equilibrium. That means the net force and the torque are both going to cancel each other out. Net force and the torque are both going to be equal to 0. And the beam is not in any danger of tipping over. That makes sense because it's in static equilibrium, right? Now, for part A, they want us to draw an extended free body diagram of the beam and show all forces, including the forces from the left and right support. So I already kind of started doing that a little bit before the meeting, just so I can kind of have an idea of what's going on to a certain extent. But we have this beam here, right? There is this right support, or this left support here, and the right support, and then you have the person over here, right? What forces can you guys name, just rapid fire real quick, that'll be acting in this system? Yep, so we have normal force, like that, right? Because those little supports there are going to help kind of push the beam upwards, right? And then there's a gravity due to the weight of the kid over here. But there's actually one other force. What do you think it is? Exactly, right? So for the FG of the beam itself, right, since they said it's a uniform beam, right, then the center of gravity, yep, so the force of gravity from the center of mass, right, since it's uniform, any uniform object, center of mass is smack dab in the middle, right? So this whole thing is 5 meters, right? Then the center of mass is like 2.5 meters away, right? So here's the force of gravity directed downwards. And I would give superscripts here to say like Earth on beam and Earth on boy or something. Well, that's B and B. Earth on kid. Let's say Earth on kid. Right? And then you can say maybe like, I don't know, left fulcrum, or left pivot, I guess. Left pivot on beam and right pivot on beam. Right? There. Oh, shoot. Yep, you're right. I forgot that aspect too. So thanks for catching that. there also should be normal force from the beam acting back up on the student, right? Because otherwise the student would just kind of sink through the beam, right? So excellent catch there. My bad. Yeah, there should be normal force acting back up on the kid as well. I think that's all the forces there. So yeah, normal force. Mm-hmm. Let's see here. So I guess. Oh, I see what you're saying. Okay, so like relative to the beam itself only, what are the forces acting on it? Okay. Oh shoot. Okay. So each support is giving a normal force acting on the beam. Okay. Yeah, then I guess maybe normal force in this case wouldn't be included then. Because this is normal force would be a force that the beam is exerting back on the person, but that's not what we're interested in. We're interested on what forces are going to be giving the beam torque. Because like theoretically, if the person goes any farther, right, this thing is going to tip over. Well, at that point, we're then not really concerned with what forces maybe that the person exerts, or that the beam exerts back on the person. So maybe just the forces that are exerted on the beam. I think that makes sense. Let me look at the rest of this problem and figure out if there's anything else here. Okay. Yeah, that's what I figured too, because like usually and in general, like I keep forgetting this rule for some reason. It's one of the easier rules to break because whenever you're drawing a free body diagram, you should only include the forces that are pertinent to what the object is feeling. And so in this case, we're only concerned basically with what forces is the beam going to be feeling, essentially. So it feels a normal force from the left-hand support. It feels a normal force from the right-hand support, right? There's a force of gravity exerted from the Earth on it, right, due to its mass. And then the boy is also exerting a force on it here on the right. But we're not really concerned with what forces it would act upon any other objects in the system. So yeah, that makes sense. Does that make sense for part A for everyone else? I just want to make sure I cleared that up because I kind of fell for that mistake as well. We good overall? Okay, cool. So part B, they want us to use the torque equation for static equilibrium to compute the force exerted on the beam from the left support. So force on the beam from the left support, so we can say like normal force L, basically. That's unknown to us. So for the torque equation, we know that since this is in static equilibrium, net torque should be equal to 0, right? And then we have what? We have torques due to gravity here pointed in the clockwise direction. Those are negative. And then torques due to normal force here, those are in the counterclockwise direction. Those are positive. So FNL plus FNR, right? These are left and right supports, minus FG of the beam minus FG of the boy, right? So this is what we're trying to figure out here. This is what we have. So 4 are, or my bad, I put, this is positive, this is torque, so I should have put torques for these, I'm sorry. Let me just erase that real quick and rewrite it. So we have torque from... Yeah. So we already we talked about this here like a minute or two ago. So this was like, we're only concerned with the forces that the beam is feeling, basically, right? So we're not concerned with the forces that the beam may be exerting on the buoy or any other objects, right? We're only concerned about the forces that the beam is feeling. So the beam feels a normal force from the left support. It feels a normal force from the right support. It feels a force of gravity due to the earth on it, and it feels a force of gravity from the buoy on itself, right? But normal force back up on the buoy is there. Don't get me wrong. It's not like fake, right? It's there. The only issue is we're only concerned, once again, with what the beam is feeling and not what it's exerting. So that's why we ignore normal force there. Does that make sense? At least, honestly, like, at least I'm fairly certain that's how it should be. Unless I'm, like, overlooking something or making a stupid mistake. But that's usually how the torque problems go. Like, I don't think I've ever seen a problem where we've had to really look at the normal force exerted back on an object from the beam or from the rod or anything like that. Yeah. So, you should have a torque due to the left support. Now, theoretically, there should be a torque exerted by the right. However, we have to indicate our pivot somehow, right? Well, choice of pivot is really important with regards to torque, and it really depends on what information you have access to, what information you're figuring out, right? So if we want to figure out what the left support torque is, and then from that figure out the force exerted by the left support, if we want to figure that out, then we want to use information that we have access to, right? Now, we have torque as well due to the gravity of the buoy. This should be minus, my bad. And then we have torque from the beam itself, right? The mass of the beam itself. Now, we can get these easily because we have the masses of both the buoy and the beam, right? We can just calculate force of gravity. And then we can figure this out here as well. Or at least that's what we're trying to figure out. Now, there's no way for us to figure out the right force or the normal force due to the right support. There's no way we can do that. We already have enough problems trying to figure out the left one. How are we going to figure out the right one? In that case, it's like having two variables that are unknown to you. It's like having x plus y, and then you have like minus 30 and minus 60, for example. Well, if I don't know x, how am I figuring out y? And if I don't know y, how am I going to figure out x? So with respect to like the torque, you always have a pivot, right? You always have kind of like a starting point. So remember the previous problem, they had this pivot here at the scapula, and then we measure distances relative to that pivot. So essentially we just have to pick a pivot here. So when you're picking a pivot, it's best to put the pivot at a location where it enables you to kind of like figure out other forces that you're interested in and minimize forces that you don't know about. So if I can figure out these forces easily, right, because I have the mass, I can calculate that with gravity, and I can figure out the torque that way, and I'm trying to figure out this left support, that's what I'm trying to figure out, and I have access to these, then it only makes sense to put the pivot at the right support. And so if I put the pivot at the right support here, then any forces acting at the pivot will not exert a torque. So normal force will be present, but it won't be able to exert a torque. The reason why is because at that point, if that's your pivot and torque is equal to the force times r times sine phi, well, regardless of what the sine is, and regardless of how strong the force is, it's at the pivot. It's at 0, right? So that's going to be like, if I literally tried to open the door and I'm only pushing on the hinge is the pivot. If I'm pushing at the hinge itself, that door is not going to move. So if I choose this as my pivot, the right support, I can eliminate this extra variable that I don't know. I can eliminate the fact that I don't know this other force right here, and therefore I can't figure out the torque for it. So if I can choose the pivot at the right support, I can still figure out what the left support is because I have access to this other information, but I eliminate any other extra forces or any other unknown information that I don't have available and that I can't figure out. So in that case, by making this the pivot, pick your pivot point where the right support is located. They give you that hint. Other times they won't give you the hint. You pick your pivot based on where you can optimize like the forces that you need to figure out and the forces that you have access to, where in general, the information that you have access to versus the information that you want to figure out, and then other pieces of information that you don't know anything about at all and you don't want to figure out and you don't know anything or any way to solve them. In this case, that would be the right support. Then you cancel those out basically and make the pivot there so you can ignore what's going on here. Like, yes, there's a force to it that we'll figure out later here in C or something, or it'll factor in later on. But the fact that it's not exerting a torque will enable us to forget about it here, figure out the torque for L, and then from the torque we can figure out the force. Because if this here then becomes 0, right? Because if we pick the pivot there, then torque of the right support is the normal force at the right times R times sine of the angle, right? Well, the angle is going to be 90 degrees, so sine of 90 is 1, so this becomes 1. R is 0. So if this is 90, if this is 100, if this is 120 newtons, it doesn't matter. Since you're picking the pivot at that right support, you're making R equal to 0, so therefore the torque is equal to 0. So then we're just left with torque from the left support minus, this will be FG R sine 90 basically, since these are still along perpendicular angles right here, 90 degrees. So this should just be equal to the weight of the boy, right? And that's 45 kilograms times 10 meters per second squared. So minus 45 kilograms times 10 meters per second squared times how far he is away from the right support. He's 0.4 meters away, right? And then we also have the torque due to the beam, right? So here, it's a little bit more difficult, I think, to figure out. So we know that in between these two supports, it's a total distance of 3. From here to here to here, my bad, is 3 meters. Well, the left support is directed pretty much right at the left end of the beam. So if I go 2.5 meters to the right, it's 2.5, right? Then the distance between the right support and the center of mass here, well, if I know it's from left support to right support, that's 3 meters. And then from left support to center of mass is 2.5. Then from right support to center of mass is just 0.5. So I can say then that the mass of the beam, right, that was 70 kilograms times 10 meters per second squared times 0.5 meters away. And that'll give me the torque for the beam. So if from here to here it's 3, from here to there it's 2.5, then it only makes sense for this area right here between the right support and the center mass to be 0.5. And the reason why we're interested in this location relative to the pivot is that's how we can get our forces, right? So if you remember this old problem here, if this was like our right-hand support, for example, then we go a certain distance away. Here's the force that we're interested in. It's 36 centimeters away. Remember, if we had here the center of mass of the beam, for example, then if this was like 10 centimeters away, then we want to figure out the distance from the pivot to the force. And so the distance from the pivot to the center of mass, where there's a force of gravity being enacted here, then we want to figure out this distance here, which is 0.5, right? Because from here to here, it's 2.5, and then from here to there, it's 3. So it only makes sense that 2.5 plus 0.5 is 3, right? So 0.5 should be the distance here. So then that gives us the torque of the left support, right? So let me calculate this out real quick. 45 times 10 times 0.4 plus 70 times 10 times 0.5. So that should give us left torque of around 530 Newton meters, right? Cool. So that's 530 Newton meters for the torque. Now, we know that torque of the left support should be equal to the normal force of the left support times the distance away from the pivot times sine 90, right? Because it's also directed directly upwards, has perpendicular angle here at 90 degrees, right? So if this is 530, and this is the normal force that we're trying to figure out due to the left support, well, then we just figure out how far is it away from the right support to the left support. Well, they gave us that, right? They said the supports are 3 meters apart. So this should be 3 meters. And the sine of 90 is just 1, right? So then F and L is what we're trying to figure out. And that should be equal to 176.67 newtons. Does that make sense for part B? It's a bit of a runaround there to go from torque to forces. 3 meters is the distance between the right support and the left support. And that's what they gave us. Does that make sense? So we're interested here in the torque of the left support, and we want to figure out the force of the left support, right? So we go, if we want to figure out how much torque this force is exerting, then we look at how far it is from the pivot, and the pivot was the right support, right? So if this is the pivot, this is 0.0 basically. Here is 0.4, right? That's how far the buoy was away. Here is 0.5, that's how far the center of mass was away. And here it's 3 meters, right? Because they said the supports are 3 meters apart. So if we're interested in this force here, well, how far is it away from the pivot? And that's 3 meters away from the pivot. How do I know the center of gravity was 2.5 meters? So they told us that from left support to right support, the distance between them was 3 meters, right? So they also gave us that the beam is uniform. They said the beam is uniform. And so the center of mass of a uniform object is just going to be straight down in the middle of the object. So if this beam was 5 meters, then center of mass is 2.5 meters, right? Center of mass is 2.5 meters. So that means if this whole thing is 5 centimeters, right? Then, well, it's not really proportional, but 2.5. You see what I mean? And so 2.5 is the center of mass there. And so if I start out as this being my 0 point theoretically, right? Then 2.5 meters away, which would be right here. So you see 2.5 meters away is my center of mass. And so if my left and right supports were 3 meters apart, then relative to the right support, the center of mass is 0.5 meters away. So 2.5 plus 0.5 is 3. So from the edge of the beam here on the left-hand side, because this is a uniform beam, then the center of mass is directly in the middle. So it should be 2.5 meters away, half the distance of 5. So if 2.5 is right here, and here to here is 3, so this is 2.5, then this little section right here, which is the R for the torque from the beam, right? That's 0.5. But yeah, center of mass is 2.5 because it's a uniform beam, so the center of mass is directly half of the distance of the object. But yeah, hopefully part B makes sense. This problem is a little bit of a doozy. I hope I didn't miss anything. I will check this problem later on as well, just to make sure that I'm like did all my calculations correct and stuff. And if there is a problem or if I made a mistake somewhere, I'll let you guys know about it. I'll make an announcement somehow. I'll probably either notify the professors or send a message on the GroupMe. But yeah, I'm fairly certain this is how it should be for B. Now, for C, actually, is everyone good with B? So I can move on to C? Or are you guys still a little bit confused? Exactly, yep. So yeah, that's what they're asking about here in part C. They're asking like, well, sure, there's no torque here because we want to make the pivot the right support, but then, all right, there's still a force exerted by that right support. And so that's what we're trying to figure out and see. What is that force that's exerted at the pivot that helps things maintain a static equilibrium, but is not necessarily providing a torque? So I'm still confused on why you use 3 meters. So like this, just this part right here. So do you understand why we made our pivot right here the right support? So if this is our right support here, this is like our origin. This is our 0 meter point, right? Whenever we're finding out torque, torque is equal to a specific force times how far that force is from the pivot times the angle at which that force is acted, right? So if we're interested in the force here, the support due to the left, right? Because this is torque due to the left support. We're interested in the force due to the left support. That's what we were trying to figure out. If I'm interested in this force and I want to figure out, well, I have the torque FNL, right? That's equal to the force of FNL times how far that force was acted times the angle at which it was acted, right? So if this is what I'm trying to figure out, I have this, I have the angle, and I have how far it was acted away. Well, relative to the pivot here, how far is this left support? They told us that the support is 3 meters apart. So 3 meters is the distance away at which this normal force is enacted. And so center of mass is just where like the force of gravity of the object is going to be acting. I don't think, I can't think of anything off the top of my head where we would use the center of mass as the pivot. Actually, yeah, no, yeah, I'm not sure if there's a specific example I can think of where the center of mass is the pivot. But, I mean, the reason why we can't use the center of mass here as the pivot is if we use this as the pivot, right, then we eliminate the option of using the force of gravity of the beam to calculate our options. Now, if we were to not make the right support the pivot, then like I said, we would have a torque due to the right support. There's absolutely no way we can figure that out. It's impossible. We don't have enough information to figure this out. Like, the idea here is that they're already asking us about the torque or the force due to the left support. If they don't know what this is, how the hell are we supposed to know what this is? That's the idea here. So that's how you pick a pivot, is you figure out like, okay, well, if they don't know what it is, how am I supposed to know what it is, right? So for this left support, if that's what they're trying to figure out, well, that's what they're trying to figure out. That's what I'm interested in too. Well, they don't even know what the right support torque is either, or what force was acted there. So there's no way for me to figure this out. They gave me information that I can figure out this other stuff. So if this is what I don't know, and I know this and this, and I still don't know this right support, then I have to make this my pivot, where there would still be a force acting there. Force still exists there. It's just that the torque is equal to the force times the radius times the sine of the angle, right? And so if I make that my pivot, the R goes to 0. Because the pivot is, like, it's essentially, like I said, imagine if this was like your hinge on a door. If you were pushing right at the hinge, it's not going to move. And that helps me cancel out this torque due to the right support, so I can figure out what the torque is to the left support and then figure out what the force is on the left support. Because otherwise, like, I'm introducing another variable. This is like saying x plus y plus or minus 60 minus 30, for example, like if we had values. So if I'm trying to figure out x and I also still don't know what y is, then that makes things difficult, because then I have to calculate for two variables and I don't have information that I can do that with. So if I make this my pivot, I can cancel out the torque here, make it an option, or no longer make it an option, right? Or a factor in my calculations. So I can easily just use these other torques and forces here to calculate the torque due to the left support and then the force due to the left support. Center of mass here, if I use that as my pivot, well, I no longer have to use the force of gravity due to the pivot anymore, or due to the beam, right? But then I reintroduce the confounding variable here of the right-hand support. So it doesn't make sense for me to cancel out a value I know in favor of a value of I don't know, right? So that's the idea here, just maximizing the things that you know, minimizing the things that you don't know. But yeah. Hopefully that makes sense. All right, sound good for part B? Left support. So based on the pivot here, right? This left support here. So imagine pushing up. So this was your pivot. These are like your hour hands or minute hands on a clock, right? If it's pushing this way, that's clockwise. Does that make sense? Now here it'd be clockwise as well, technically, right? Yeah. This would be downwards like that. Clockwise. So yeah, I guess in this case, torque should be negative. Yeah. Yeah, that's a great point. I made that mistake. Thanks so much for catching that, because technically these shouldn't even be negative torques. They should be positive. But that's not a huge issue, because it's just a matter of like, this is addition, 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 and there should be a negative torque here, because these forces here, actually, hold up. So, okay, now I have to go back and look at this real quick. So, man, totally forgot about the clockwise and counterclockwise directions, damn it. So if this is our pivot and we're going this way, this is a clockwise direction, right? So if it's clockwise, it should be negative for the force of the buoy. Oh, hold up. Yeah, clockwise for the force of the buoy. Yeah. Or for the torque of the buoy in that case, right? And then for the beam, like that, that pulls it in what? So if I were to imagine this, pulling it down like that, That's counterclockwise, so that's positive. Okay, well, that significantly changes things up. So boy should be negative, beam should be positive. All right. Now, normal force due to the left support here, that's also in the clockwise direction, so that should be negative. So, let me recalculate this real quick. So we have negative 45 times 10 times 0.4 plus 70 times 10 times 0.5. So this should give you a be 170, I guess. This is in terms of the magnitude, by the way. Magnitude of the, this would give you magnitude right here. Because if we plug this in with the directions integrated, it would be negative 170 newtons. Well, that makes sense anyway, because it's moving in the clockwise direction. So clockwise, this is clockwise still, but then this, right? So I imagine like if you were to let go of everything else and allow this force here to kind of take over and tip. So it would kind of go like this way. And then that would be clockwise as well. So that's negative. So negative for the beam. Wait. No, that's counterclockwise. I'm sorry. That's counterclockwise. That's counterclockwise. Counterclockwise, so that should be positive. Jeez. Okay. Yeah, so clockwise for the buoy. Counterclockwise for the beam. I'm just making sure. I'm going to go over this one more time. Yeah. Counterclockwise for the beam. That's positive beam, negative buoy, and then the left support goes in the clockwise direction. So that should be negative as well. So you end up with 170 Newton meters, okay. So this should be 170, right? That should be 3 still, but instead of 176 newtons, it should be 170 divided by 3, so this is 56.67 newtons, I guess. So torque due to the left side is negative in general. It's just that when you're calculating things, since we integrated the direction here, when you add it over, this is positive T and L, right? And so when you calculate the rest of this, you get a positive 170. So this just gives you the magnitude at the end. When I integrate the directions in my equation, I get the magnitude. But if we were to just ask what the torque is on the normal force here for the left support, it should be negative torque there. And so in that case, with regards to that, this should also be a negative force technically, I guess, but since it's directed in the positive direction, we should keep it positive, basically. Since it's along the positive y-axis. I think that's everything for part B. Mistakes included, I hope. But the way that this problem is going, it's not looking too well. So I apologize if I've caused any confusion. After this session, I'll look over if I've made any mistakes, just because sometimes during the sessions, like, I'll just be blinded to certain things. So if I kind of go over it later and I'm like calmer and stuff, then if I find any mistakes or anything like that, I'll for sure let you guys know. But I don't see any other issues, at least I don't think, for part B. But yeah. For that force, you mean? The force for the left support? Yeah, so for the beam, since the beam right here is pulling you down like this, so if I think about this as a clock, if I'm going this way, right, then I'm going counterclockwise, and that's positive. So that's why I added a positive sign right here. And then for the buoy, once again, if it was a clock, right, pulling down like this, then that's clockwise, not counterclockwise, right? So clockwise is negative, counterclockwise is positive. So that's why clockwise for the buoy, it was negative, and for the beam, counterclockwise was positive. But yeah, I think that's pretty much it for B. For C, it says use the force equation for static equilibrium with your answer above to compute the force exerted on the beam from the right support. So if we have F net Y, right, then we have an F net or F normal from the left support plus from the right minus gravity of the buoy minus gravity of the beam. Right, and so we have this being 56.67 newtons. This is unknown. And then weight of the buoy, right, that was just 45 kilograms times 10 meters per second squared. Right, that's just the weight. And then for the mass of the beam, or the weight of the beam, should be 70 kilograms times 10 meters per second squared, right? And then that should give us what? Let me figure that out here real quick. 6.67 minus 45 times 10 minus 70 times 10. Yeah, 45, 70. Yeah, so that seems absurd, but I'm getting like 1093.33 newtons for that. So right support is somehow exerting that much force, I guess. That sounds insane, and that makes me doubt what I'm doing for problem 3. But I will update you guys if I see any other mistakes in problem 3. Geez, this by far I think is the worst problem that I've done so far. And it shouldn't be. I don't know why it's such an issue. Usually I'm like really good with torque, but for some reason this one has been giving me trouble. I guess I just kind of overlooked some of the counterclockwise, clockwise stuff. But I think that's... Yeah, I mean, but you still have to include the directions of what's going on. Remember, because like in the Tom and Jerry problem, right? It really mattered what the direction is to figure out what the forces are and what's going on. So you have to factor in the direction of clockwise versus counterclockwise. That's non-negotiable. Like you don't have to have an angle for, or I guess you don't have to have like an angle that kind of directly gives you a change in the torque. So like, I guess what I'm saying is like, for these problems initially you had 60 degrees and 80 degrees, for example. Even if they were 90 and 90, right? You'd still have to factor in if it was clockwise or counterclockwise, because otherwise, if you just made it T Tom plus T Jerry, then it's not going to work out the right way. You'll just get an incorrect force, basically. And so that's why it's important, I think, to make sure that you're factoring in the counterclockwise, clockwise stuff. So definitively, counterclockwise is positive. Well, that doesn't look good. Positive. Clockwise is negative. So if I'm looking at this aspect right here, I'm going this way. That's clockwise. So the torque for the boy clockwise is negative, right? So we made it negative. Now, for this point right here, the beam, right? The way I think about this one is, okay, if we were to let this go, if we were to let this center of mass kind of overcome everything else, and like kind of like a seesaw, right? If it went this way, if it plopped down, right, like a seesaw, if it plopped down in that direction, then we're going this way, this way, this way, this way, right? That's counterclockwise. So that makes that aspect here positive. So if that's the case, then the torque due to the beam is positive, and we kept it that way. And then we know that the torque here for the normal force due to the left support, if we were to also kind of let that overwhelm things, right? If we went like this, right? Like that, then you're going this way, this way, this way, this way. That's clockwise. So that's negative. That's why we made the torque here negative. And when we add things together, when we add this to the left side and calculate the rest of this out, we get T and L is equal to 170. But we integrated the direction here anyway. So yes, T and L, like in general, should be like negative 170, right? It's exerting a torque in the clockwise direction, which is negative. And then with regards to the force here, since it's directed along the positive y-axis, we just keep it as 56.67 newtons, right? Because the rest of these are directed along the negative y-axis. And so then that's how we integrate them here in the F naught y equation for C. At least that's how it's looking so far, unless I made any mistakes, which honestly, I'm just going to be honest, like I am expecting for there to be something that I screwed up. But especially considering the absurdity of this answer. So I will go back and check for sure. But for now, I guess at least you understand like what's going on with regards to torque. But that's problem 3. Yeah, that one took a lot longer than I was expecting. So I'll just move on to problem 4 real quick. Problem 4 is a lot easier, I hope. This one was an exam problem, I think, that we had before. And so, give me 1 second here. So this was beam of length 5 meters is hung from the ceiling with 2 strings, okay? And then the mass of the beam is small enough that you can neglect it. The beam has 2 masses attached as shown in the figure, and the system is in equilibrium such that F net is equal to 0 and T net is equal to 0, right? That's not bad. They want us to draw an extended free body diagram. So we have one like this. We have the beam. We have tension force 2 like this, tension force 1 like that, both pointing upwards, right? Pulling it upwards. And then you have these masses here, right? Force of gravity due to the first mass and force of gravity due to the second mass, right? So some people might think that, oh, well, there's a rope attached, so it's like tension or something, right? Well, sure, but in reality, what's kind of pulling down really on this, on the beam here? It's the mass, the gravity of the block here, 2 and 3. That's what pulls down the beam in the negative y direction. So that should be your free body diagram. This is 1 meter away. This is 1 meter away, basically. And then the entire length, like they said, is 5 meters, right? And yeah, no normal force from the weights. The weights aren't in contact with a surface, right? And once again, with regards to normal force, as a contact force, remember like what we had with problem 3, where someone was suggesting that we should have a normal force like that. We're only interested in what the beam is feeling, because we're interested in how this beam rotates, if it's going to rotate clockwise, if it's going to rotate counterclockwise, or if it's going to stay static, right? If it's not going to move. So we're not interested if, for example, if there's a block sitting on the beam, we're not interested in the normal force that the beam exerts back on the block. We're just interested in the force of gravity that the block is exerting on the beam, basically, or that the beam is feeling from the block. But yeah. And normally, if this beam had a mass, right, it would have a gravity, it would have a weight, right, and we'd have a center of mass associated with it. But they said that the mass of the beam is small enough that you can neglect it. And so that's why you don't include a center of mass or a force of gravity due to the beam itself. Otherwise, if it did have a mass that was significant, then we'd have an additional force of like Fg beam pointed downwards as well. Does that make sense so far? Cool. Now it says use the torque equation for static equilibrium to solve for the magnitude of the tension force, Ft1, right? So, once again, if we're using torque, we have to define some pivot first, right? So if we're interested in Ft1, that's what we don't know. We can figure out the mass of this, or we can figure out the weight of this, and the weight of this, right? We can figure out the forces of gravity due to each one because we have the mass. But we also don't know what Ft2 is. Well, if we're trying to figure out this one for sure, and we also don't know this one, then we can make Ft2 here our pivot to where the torque for Ft2 no longer factors into our torque equation. Because then we would just figure out the torque due to Ft1, the torque due to this mass, the torque due to that mass. We can figure these two out, we can calculate them out, and then solve for the torque due to Ft1. And then from the torque due to Ft1, we can figure out the force of Ft1. And then that's it, right? So that's the hint that they gave you. Choose the pivot at the right end of the beam. With that choice of the pivot, the torque from Ft2 would be 0. Because any force acting at the pivot, it would have an R of equal to 0, right? And so then you no longer have a net torque at that point, or torque at that specific pivot. So if we say net torque here is 0 because they said it's in static equilibrium, T net is equal to 0, then there is a torque due to Ft1 here. And we have to, once again, indicate that, okay, if this was our pivot, and this force kind of pulls it upwards, right? Well, that direction is kind of clockwise, right? So, it should be like negative T Ft1, right? That's clockwise. And then we have these two forces for gravity pulling things downwards, right? This was a clock, pulls it downwards like this. Oh, it's frozen? Okay, one sec. Okay, is it good now? Okay. So yeah, for tension force 1, clockwise like this, that's negative torque. And then for these forces right here, they're pulling things downward, so it's like this. That's counterclockwise, right? So torque due to Fg1 and torque due to, oops, Fg2, right? So it's like if I were to cut the rope, for example, then these forces would help pull that beam in a counterclockwise direction, right? So that makes them positive. Counterclockwise is positive, clockwise is negative. Fg2 would still be going counterclockwise, I'm pretty sure, because if this is your pivot here, it would be pulling it down like that, counterclockwise. Yep. Does that make sense so far? Any questions at all? Nope. Okay. So now we can calculate T of Ft1, and that's equal to just the combination of these forces here, or these torques here, right? So we have torque due to Fg1, right? We have this weight here that's 2 kilograms times 10 meters per second squared, right? And then this is, we can add that to the torque due to Fg2. That's 3 kilograms times 10 meters per second squared. And then move things over here, I forgot to add. This is times the radius for this one is, this one right here is 1 meter away. It's frozen again? Okay. One sec. There. Was that good so far? Can you guys see? Okay. So this Fg2 is enacted at 1 meter away from the pivot. And then since this is 1 meter away of the end, this whole thing was 5 meters. So it only makes sense from here to here to be 4 meters. So Fg1 would be at 4 meters relative to the pivot here. This is 4 meters. And then right here is 1 meter. Right? It's 1 meter. And then I didn't put the sine 90 there because sine 90 is just equal to 1. These will both have a 90-degree angle there, right? So, for the torque for Ft1, should be I got 110, I believe, Newton meters. All right. And then from that torque, we can set that equal to ft1 times r for ft1 and times sine 90, right? So we can just divide by 4 in that case, I believe, and you should get around T1 should be 27.5, I believe, 27.5 newtons. But I feel like something is a little off here. But yeah, did everyone else get that for B? Anybody see any issues with that? Or is it all making sense? I put R as 4 because if this whole thing is 5, right, and here is just 1, and here is 1, right, at this point, then this distance from here to here is 4, because it would be 4 plus 1 would be 5. So I had my R as 4, so I did 110 divided by 4. Phenomenal. This is just a great way to end off the session, honestly. Oh shoot. See, yeah, now I knew something was off. So it would be, yeah, it would be 5 meters. Because I was thinking of this position here. I'm interested in FT1. I don't know why I did that. That's 5 meters for sure. Yeah, so 110 divided by 5. That should give us 22. Yep, okay. FT1 is 22 newtons. My bad. It should absolutely be 5 because FT1 is at 5 meters relative to the pivot. Pivot is here. This is 5 meters away. So R is 5. My bad. But yeah, FT1 is 22 newtons. That's solid. Okay. Sound good for part? I'm like, this is 100%, right? I'm like, I don't have a doubt about this one anymore. Because I just messed up the R for the last part. That's all. Sound good for part B? Okay, cool. Now part C is just a lot simpler because then we're just using the force for static equilibrium to figure out FT2. So it's just looking at how all these forces cancel each other out, right? So F net Y is just FT1 plus FT2 minus FG1 minus FG2, right? And we already determined this to be 22 newtons. We want to figure this one out. And this will be 20 newtons, and this will be 30 newtons because it's 2 kilograms times 10, and it's 3 kilograms times 10. So minus 20 newtons minus 30 newtons, right? And they want us to figure out the absolute value for FT2. You're going to end up FT2, I think, as what, 22 minus 50. So you'll get 28 newtons for FT2. So FG1 and FG2 are negative since they're directed along the negative y-axis. Yes, they provide a counterclockwise direction, and that gives them a positive torque, but they're directed along the negative y-axis. And that's kind of the distinction here. The issue here is that, yes, the torque is negative in a sense that it helps you move in the clockwise direction, but the force itself is directed along the positive y-axis. But yeah. So adding a negative or a positive to your torque values will just depend on what direction it's in, counterclockwise or clockwise. But direction of forces would just be negative y-axis, positive y-axis, like that. So that's the written homework, I think, for all of that. Like I said, I'll check in on problem 3 again, just to make sure that I didn't mess anything up on that one. And I'll let you guys know, hopefully before tonight, before the end of tonight, basically. So you guys have enough time to make any edits for tonight and for tomorrow as well, since the homework is due tomorrow. But yeah, that's been it. With regards to the online homework, I'll probably do a session just on Tuesday with that quiz review and just go over some of the online homework on that Tuesday quiz review. But that's it for the written homework. Hopefully I didn't miss anything up for problem 3, but problem 4 I'm pretty sure is spot on, and problem 1 and 2 were spot on as well. But yeah, no problem. And I'll end the recording on that note. Yep.